Okay, we are recording. And let's see. All right, so if I remember right, we left off last time with column designs, and we had learned how to do the interaction equation or diagram, interaction diagram, where you have the axial load on the vertical and the moments on the horizontal. And let's see. I got the group chat and I got participants. Here we are. And sorry, bear with me. And somebody's adding. Okay. All right. So if you remember from last time, we learned how to draw an interaction diagram, and we did it with a minimum of 5 different points. And we calculated where the pure axial is. We calculated where there's no tension in the rebar. We calculated the balance condition. We calculated where epsilon sub t is 0.005, and we calculated where it was pure moment. And those gave us a diagram that we could use to plot. Okay, so now what we're going to talk about is design, using design aids. So there are some design aids that we can use to kind of help us if we don't know what column we're looking for. In other words, what size of column, what steel is required, that sort of thing. Quite frankly, in the real world, we don't use design aids because of software now is so fast that it's actually just faster to just start guessing. And you really hone in on an answer pretty quick just by choosing a size and then make it a little bigger, add a little more steel. Does this look reasonable? Okay. And that's really the way we do it. But if you had to do it by hand, like the examples that we did in our last meeting, then it probably would make sense to have some kind of a design aid to help us. So in the textbook, in Appendix A, has reprinted some ACI charts for column design. Like I said, in the real world, ACI doesn't really print these anymore because the way that software works is so much quicker and so much more accurate. But this is just to give you an idea of what the design process looks like. To use the charts, we have to establish these parameters, K sub n and R sub n need to be established. K sub n is equal to P sub n over F prime C AG, where Pn is equal to Pu divided by phi. So this is really a required Pn as determined by the demand divided by phi. And Rn is equal to Pn times E F prime C over AGH, which is really pretty close to the same Rn that we use for beams. The Rn that we use for beams is Mu over F prime C BD squared. So this is really very similar, just using slightly different variables. Or Mn over F prime C AGH. This definition is different than used for beam design. and Mn is equal to Mu over phi. So using an example, here's our column again that we had last time, a 16 by 16 column. F prime C is 4,000 PSI. Assume a tied column. Fy is 60 KSI, and Pu is 400 kips. Mu is 200 kip feet. And what is required is repeat example 1 using F prime C equal to 4,000. Use the tables to find the required steel. So in this case, I'm not giving you the steel. We have to design how much steel we need to satisfy these loads. So Kn is P sub n over F prime C Ag. Pn is Pu over phi. For here, because this is a tied column, we're going to use phi equal to 0.65 for these. You wouldn't start this with a phi of 0.9 because you're probably not going to be in that part of the interaction diagram where it's tension controlled. You're with a Pu of 400, you're going to be in the compression controlled region. And it's always better to start off conservative. And if you can bump it up, then you can bump it up later. So Pn is 400 over 0.65, which is 615.4. Kn is Pn F prime C over Ag, so 615.4. 4 KSI 16 squared is 0.601. Rn is Pn E over F prime C AGH. E is Mu over Pu. 200 kip feet times 12 over 400 is 6 inches. So Rn is equal to 615.4 times 6 inches over 4 KSI times 16 is Ag times 16 is H, 4.225. Gamma, if you when we get to the chart, you'll see that you have to define a gamma. Gamma is the distance between the bars. So the distance between the bars the distance between the bars divided by the overall width. So 16 minus 2.5 minus 2.5 over 16 is 0.69. So the problem most closely matches graph 3 on page 620 of your textbook, where rho is equal to 0.034. I thought I recreated that diagram. Where did I put my, sorry guys, looking for my textbook. Okay, so page 620. So we're looking at Appendix A, page 620 in your textbook. And rho is 0.34. Is, okay, so six number 11s. There it is. Okay, I knew I had it in there somewhere. Okay, sorry about that. So I've recreated the chart here. We found that Kn was 0.605, I think it was, and Rn was 220 something. And so you plot these together onto the chart, and then you have to interpolate between these two bars. This diagram, the lower one, is a rho of 003. The larger, the upper bound is 004. So what I did is I drew a perpendicular from the 003 to the 004 and interpolated. And I got that should be about 0.034 from what you see on the screen right there. So if I go back, Okay, so I had 615 for, I'm sorry, 601 for Kn, 225 for Rn. That's how I interpolated to get 034. And then the area of steel is 034 times the gross area. 16 times 16 is 8.7 inches squared. And so if I choose 6 number 11s, I have 9.36 inches squared. Even though I show 8 bars, 6 bars, I just put 3 in each row. Okay, so then, still example problem number 2, verify rebar solution. And here's my 6 number 11s in this column, and I plotted out the interaction diagram, plotted out my load point of, let's see, it was 400 up and 200 over, and it's inside of the chart. So it is confirmed that it's working. Or you could hand calc out those 5 points again and confirm that it would work that way as well. Oops, the wrong way. 6 number 11s works. Okay, any questions about that part? Any questions at all about how to use the design charts? Okay. Then we're going to move on to the next section, which is shear, column shear. ACI 318 equation 22561 can be used, but can be actually very conservative for columns with an axial load. So in beam shear, we had this equation that was 2 lambda square root f prime c BWD. We can use that equation, but it's overly conservative. You're really losing out a lot because the axial load in a column augments the shear capacity quite a bit. So if we use equation 22551 for columns with axial load, you get a much better answer by using this equation. ACI 318 table 22561 offers a more detailed method for calculating VC for columns with compressive loads. And you can use the lesser of A or B, where A is this animal, where you have 1.9 lambda square root f prime c plus 2500 times rho w times VUD over mu minus nu times 4h minus d over 8 BWD. Not applicable if mu minus nu over 4hd over 8 is less than 0. Or B, we can use 3.5 lambda f square root f prime c BWD times square root of 1 plus nu over 500 ag. So you can use the lesser of these two. These are not totally simple equations, but they give you a much better answer than this is the simplest one. Or you could use 2 square root f prime c is the very simplest one, but that is grossly over conservative. Where Nu is the axial load and is positive for compression. Okay, so given an example here, I have a column. F prime C is 5,000 PSI. It's an 18 by 24 column. My shear is coming in this direction. And my D is 15.5 as measured from the steel to the face there. Rebar 60 KSI. For those of you who just joined, can I ask, please try to get here closer to 5 o'clock. It is somewhat an interruption if you show up late, please. Okay, so F prime C is 5,000 PSI, Fy is 60 KSI, the axial load is 400 kips, and my moment is 200 kip feet. I have a shear load of 125 kips required. Using number 4 grade 60 ties, what is the required spacing to satisfy the shear demand? So if I use the simplified equation 22561 or use table 22561. Solution. So to find the capacity of the concrete alone, VC, I use this equation. This is actually the simpler of the ones, where if I plug it in, I have 400,000 pounds over 2,000 times AG is 24 times 18. Lambda is 1, 5,000 PSI concrete. My width is 24. My D, as shown here, is 15 and a half. So VC is 77 kips. S required is AV FYTD over VS is equal to AV FYTD over VU minus VVC over phi. We covered this a couple lectures ago in our shear demand. And so if I plug in my numbers, I have 2 legs of number 4 tie times 60 KSI times D is 15 and a half. My demand is 125 minus phi is 0.75 times 77 that I found here over phi. And that all equals 4.15 inches on center. So I'm going to use number 4s at 4 inches on center. So phi Vn is phi Vc plus phi Vs. Phi Vn is 0.75 times 77 plus 0.75 times AV Fy D over S. And I get 127.5 kips, greater than 125 kips, so we're okay. Part B, find the capacity of concrete alone, VC, and we're going to use the lesser of the 2 equations from that table. Okay, so mu minus nu, 4h minus d over 8 is 200 kip feet times 12 to get the kip inch, minus 400 kips times 4 times 18 minus 15.5 over 8 is minus 425 kip inch. So this is not applicable if this is under 0. So equation A is not applicable here.
Professor?
Yes.
So for our axial design, our PU is considered MU. I mean NU in our case. Because
Yes.
for
Yes.
NU you're using the 400. That's why.
That's right. Yes,
Okay.
that is correct. So
Perfect.
the reason I think that they didn't write the equation with PU, they wrote the equation with NU, because generally in concrete design, if it's compression, we say PU is equal to 600 kips. That's 600 kips of compression. But if we have net tension, we say TU is 600 kips of tension. It's weird, but we kind of use TU if it's in tension and PU if it's in compression. They want this equation here to be good for either tension or compression. So they use NU. And then they just say that NU is positive if the column's in compression. I think that's why they did that. Okay, so the other equation, equation B, 3.5 lambda square root F prime C BWD times the square root of 1 plus NU over 500 AG. So I just plug in F prime C, BW, D, NU is 400,000, again, positive it's in compression, 500 times AG, I get 155.5 kips. So my S required is AV FYTD over VU minus VVC over phi, like we did before. Only now I have 155 kips in here. And that gives me 33.3 inches. ACI 318 table 97622 prescribes a maximum spacing of S is D over 2, or 15.5 over 2 is 7 3/4. So I can use number 4s at 6 inches on center. But look at this. I got 4 inches on center required before. Now I get 33 inches on center. That's because VC virtually doubled. So that's the difference between using a simplified equation and using the more elaborate, sophisticated equations. So now we check our work. Just like we always check that phi Mn is greater than Mu, we check that phi Vc is greater than Vu. So phi Vn is 0.75 times 155.5 plus 0.75 times AV Fy d over spacing of 6. And this gives me 163.1 kips, which is greater than 125 kips, so we're okay. Any questions on that presentation?
So, Professor,
Yeah.
would you want us to use the sophisticated method in this case because it's more economical?
Well, of course, there's always the difference between what would you do in a real life design and what would you do for homework or an exam situation. I would think that if I don't specify, then you can use the simplest equation that is applicable, which in this case would be, let's see, where were we? Here. Okay, so this equation is meant for columns, and these two equations are meant for columns. So if I don't specify to use this one or this one, then you can use the simpler one.
Okay, makes sense. Thank you.
Okay. Any other questions on column design? Okay. Then what we're going to do is we're going to switch over to today's lecture. This is lecture 12. Okay, so here we go. Today we're going to talk about slender columns. So far we have talked about columns with concentric loading, no moments. Then we talked about short columns with applied moments. And now we're going to talk about slender columns that could have applied moments as well. A long, slender member carrying compressive load is known as a slender column. We can start with a pin-pin supported column of an unbraced length L sub u, like so. So the unbraced length is from support to support, and the supports are pinned. They offer no flexural resistance. And we can have an applied moment like so, and an axial load. If we add a factored axial load P sub u and factored moments M1 and M2 as shown, and ACI code defines M2 is greater than M1. So whatever the end moments are, M2 is always the bigger one, M1 is always the smaller one. Then we get the following axial load and moment diagrams. The axial load diagram is a consistent PU, and the moment diagram could look like this. Mu is the lesser moment, M2 is the greater moment. The applied moments will cause a column deflection as shown, like this. So if I put a twisting moment here and a backwards twisting moment here, you're going to bend the column out of plane, like so. This deflection is labeled as delta. So I have a deflection of delta from the applied moments. The axial load now has an eccentricity at the midspan of the column equal to delta, which produces an additional moment equal to P delta. So this is the moment diagram due to just the axial load times the eccentricity. So where the eccentricity is greatest, I have the greatest P delta moment. Where the eccentricity is equal to 0, I have 0 added moment. So this is just the added moment due to the deflection of the column. This additional moment adds directly to the originally applied moments M1 and M2. So now I have M1 is still what it was, M2 is what it was, but instead of that straight line, we now have this added. I've added this to the previous diagram. So this is the total. The combined moment, MU, then produces even greater deflections, which in turn cause greater moments. Depending on the degree of slenderness and the magnitude of the original moments M1 and M2, this cycle may converge to an answer, or it may prove to be unstable. In other words, it may or may not catch itself. It could collapse. ACI 318, section 6645 for non-sway and 6646 for sway columns eliminates this iteration process by introducing the moment magnification method. So in other words, they came up with a method that approximates this behavior, but it really is an iterative behavior, and it either catches itself and converges, or it doesn't catch itself and it doesn't converge, which in the real world would mean that the column actually bent out so far that it fails. It collapses due to bending out too far. The moment magnifier method uses a factor delta to amplify the M2 moment to a final design moment M sub U. Okay, do I have any questions so far? Okay. So critical to a column slenderness ratio is what's known as the unbraced length. Typical concrete columns are braced against buckling at each floor line. The unsupported column length L sub U is the height of the column from the top floor below to the underside of the supporting slab, beam, or column capital. Depending on support conditions, there may be different unsupported column lengths L sub U in each coordinate direction. You could have a different unbraced length in the east-west direction as opposed to the north-south direction, depending on the circumstances. Effective length factors. You remember this from mechanics of material when you talked about column buckling? The factor K is introduced to create an effective length of column when support conditions other than pin-pin exist. And of course, in the real world with cast in place concrete, rarely ever do you actually have a pin-pin condition. If the columns are braced or non-sway, K is going to be less than 1.0. If the columns are unbraced or sway columns, then K is going to be greater than 1.0. And sorry for the confusion, braced or non-sway, I think ACI uses the term non-sway, but AISC for steel columns uses the term braced. And it kind of, you can consider them to be interchangeable. A brace column is exactly the same thing as a non-sway column. An unbraced column is exactly the same thing as a sway column. So some examples of support conditions. If you have a true pin-pin condition, then the bent shape kind of follows the shape of a sine wave, and k is equal to 1. You remember all of this braced stuff? I think I'm going to show you some of it, but it all comes from Euler's equation for a critical brace length or a critical buckling load. That's what it was. Euler's equation for critical buckling load was based on pi and sine waves and differential equations of sine waves. So one full sine wave is k is equal to 1 for pin-pin condition. If you have a fixed condition, then there's no deformation, there's no slope to the deflected shape at the top or bottom. And so the effective sine wave is actually half of the effective length. So for fixed conditions, k theoretically is 0.5, but the authors of the text suggest that you should use a k of 0.65. You don't want to underestimate this. So you want to be a little on the conservative side. So k suggested is 0.65. Because some support conditions are difficult to develop in a real structure, suggested values for k might need to be a bit more conservative than the theoretical. If you have a pin fixed condition, k is 0.7. K suggested is 0.8. Brace frame columns can always conservatively use k equal to 1 without further analysis. In other words, if your columns are braced against sway, you can always use k equal to 1. You're just going to be on the conservative side. For unbraced or sway columns, these are columns that are not relying on some other structural element to keep the building upright. So remember we talked about last time, we talked about the concrete parking garage at Cal Poly and how some columns are part of the moment frame and other columns are not part of the moment frame. They're just tied all together with a concrete slab. Well, the columns that are not part of the moment frame are braced or non-sway columns. They're braced by the moment frames. But the columns that are actually in the moment frames are not braced. They brace themselves. So those would be considered unbraced or sway columns that are making up the moment frame itself. And when those deflect, you get a very different shape. So for a fixed side sway condition, so in other words, the column is fixed at the bottom, the column is fixed from rotation at the top, but the whole column can sway back and forth, then this is a theoretical 1.0 K, but it's suggested to use 1.2. For a fixed pin side sway condition, so same thing as before, but now we're pinned at the bottom, fixed at the top, but they can sway to the side, then K theoretically is 2. The suggested value is also 2. For a fixed free condition, where this is basically a flagpole, right? You're fixed at the base and you're totally unsupported at the top, then the deflected shape takes on this curvature where the sine wave is twice the height of the column. So the theoretical K is 2, but the suggested K is 2.1. Braced or unbraced? Okay, so here's the question we've been talking about. If your column is part of a system that is braced by something else, a shear wall, moment frame, brace frame, whatever, then as these deflect, notice that they can't laterally deflect. They can only deflect straight down. And so this is a very different shape than a sway column. Okay, does this make sense to everybody? It's not allowed to deflect laterally, so it's being held in its position laterally, but it can deflect out of plane due to the loads. As opposed to a unbraced frame, see, this one is braced by some element. These columns are only braced by their own stiffness, so they can bend out of plane as well as bend under the axial loads. Okay, so can everybody see the difference between these two? And it's a huge, huge difference. These guys can take a lot more load than these guys can if it's braced or unbraced. Okay, so here's the deflected shape of an unbraced frame. ACI 318 presents several tests for braced or unbraced criteria. ACI 318.625 says that if a bracing element has a stiffness of at least 12 times the gross stiffness of all columns in that story, then those columns are braced. ACI 6643 offers two tests. Test number A, or test number 1, the increase in column end moments due to second order effects does not exceed 5% of the first order moments, then it's braced. Or Q, in accordance with 66441, does not exceed 0.005. And this is Q. Q is the sum of all axial load on that story. This is the deflection of that story. This is the shear that caused that deflection. And this is the story height. And here's the definitions as I just mentioned. In practice, most of these tests are not necessary. It will be, well, I obviously can't spell, but it will be obvious which columns are braced or unbraced. But you could have a situation where maybe it's not clear, and you can use any one of these tests to, what you're trying to do really is prove that you have a braced system. But if you can't prove that you have a braced system with these tests, then you have to design them as an unbraced system.
Professor, how
Yeah.
do you prove that you have a brace system? Don't you have to have like moment connections for the connections for them to be braced? You can't just put pin connections and assume it's braced, right?
Okay, great question. And let me do some scribbling here. Let me do a little bit of scribbling. So here's my column, right? And usually what we're talking about is this column is not part of a moment frame. If this column was part of the moment frame, then it would just be hands down an unbraced column, because moment frames rely on their own stiffness to keep themselves up. So generally speaking, we're talking about a column that is not part of a moment frame, but may have a concrete slab that is cast around it. And this concrete slab is tying this column to something. Most of the time, as I mentioned, most of the time it's obvious whether or not this column is tied to something that is sufficiently stiff to make this column believe that it is braced. But sometimes you could get, and it's a very strange situation, but you could have a situation where it's not clear. Is this braced or is this not braced? The situation I can think of just offhand might be something where maybe what you have over here is a steel system. Maybe this is tube steel. And it looks like, I can't do that, can I? And maybe these are rods, tie rods. You know, like, well, everybody went to high school, right? I'm not sure if everybody's high school had grandstands for the football stadium or the track stadium or whatever it was, but a lot of those steel structures that are the stands that you watch around the field have these guy wires or these, I don't know, 3/4 inch thick steel rods that X brace the system. Okay, so that's what I'm kind of thinking about here, like fairly light gauge steel with X bracing. That's the lateral system. And this is the column that we're not sure is that braced or not braced. If this was a shear wall, this is braced. If this was a moment frame made out of concrete, this is braced. But if this is a rinky-dink two steel brace frame with 1/2 inch or 3/4 inch steel rods as X bracing, this may not be braced. Because if this thing tries to sway out, if this column that we're designing tries to do this, how stiff is this frame to keep it from doing that? This is where you have to do your test, because we can't just eyeball whether or not this little rinky-dink steel frame is stiff enough to make this concrete column feel like it's braced. If this is so flexible, it might actually be more flexible than this column itself, in which case this column is stiffer than this frame, then it most definitely is going to be unbraced. Does that make sense?
Yes, it makes sense. I only thought that if it was like moment connections, then that's it, it's braced. But now that you put it this way, it clicked. Thank you so much.
Sure, sure. Now, if it has moment connections, like you said, like a terrible sketch, but let's say this is your column. I'm doing a terrible job, but okay, say like this is your frame and you're trying to design this column, then this is most definitely unbraced. This is a moment connection, moment connection, moment connection, moment connection. But this whole frame is unbraced because it's relying on its own stiffness to keep it stable. If this frame was tied in to something else that is a lot stiffer than this frame, then this frame could be considered braced. But usually that's not what you have. You don't go to the expense of making a moment frame if you're going to tie it into a shear wall or something that's even better. You're kind of throwing out your money. So does that help?
Yes, it makes sense now. Thank you.
Okay, okay, great. Any other questions about this topic? Okay. Where were we? There we go. Okay, so as I said, in practice, most of these tests are not necessary. It would be obvious which columns are braced or unbraced. That condition where I drew a concrete column being braced by a light gauge steel brace frame is like the only thing I can imagine that would be an example of where you're not sure. In the Cal Poly parking garage, absolutely crystal clear. Every column that's part of a moment frame is unbraced. Every other column is braced. Simple. Okay. In lieu of using K values from the charts as I gave you above, a more accurate answer can be found from using alignment charts. ACI 318, figure R625A. The R stands for reference, which means it's not legally binding that you have to use that figure. Anything with an R in front of it is reference, but it is a good reference. So reference figure 625A can be used for non-sway, and 625B can be used for sway columns to find the value for K. Each of these charts uses a psi value, psi A at the top and psi B at the bottom of the column, where psi is equal to the stiffness of the sum of all the columns over the sum of the stiffness of all the beams. So the top is the sum of stiffnesses of columns, including the column that you're designing, and the bottom is the sum of the stiffnesses of the beams framing into the joint in the plane to the direction of interest. L sub C is center of joint to center of joint of the column. I is center of joint, or I'm sorry, L, that's L there. L, center of joint to center of joint of the beam. Psi is equal to infinity for a pinned condition, but we usually take it as 10. Psi is equal to 0 for a fixed condition, but we usually take it as 1. For the psi equation, there are several choices for the moment of inertia of columns and beams. So you got to plug in right here, I sub C and I sub B, you got to plug in the moment of inertia for the beams and columns. In concrete construction, as we've said several times now, it is normal, anticipated, and acceptable that the concrete is cracked. It is normal to understand that the beams are going to be cracked. Even the columns with some axial load will be cracked as well, but they won't be as cracked as the beams are. So we have to account for that in some way. For laterally loaded structures, ACI 318 section 66312 allows for the simplest version where I is equal to half of I gross. But in the psi equation, the half factor would divide out, and so this equation really isn't applicable for this application. So we need something a little better than that. ACI 318 section 66311 offers a bit more realistic values for the moment of inertias. Table 66311A offers, for columns, you can use 70% of I gross. For beams, you use 35% of I gross. Additionally, ACI 318 66311 prescribes to divide the column moment of inertia by a factor of 1 plus beta ds, where beta ds is the ratio of sustained shear to total shear in the story. Usually, most concrete structures do not have a sustained shear, usually. Or if they do, it's pretty small. Most of the shear in a column is going to be from wind or seismic, and neither of those two are sustained. I really have a bad habit of explaining something, and then I wrote it right after. However, rarely is there a sustained component of story shear. Usually a story shear is transient, such as wind or seismic. Okay, so alternatively, ACI 318 section 66311 and table 66311B give more accurate values for the moment of inertia. Columns are 35% IG, less than, and you got to fill in this really nasty equation, but it's at least 35%, but not more than 87.5% of I gross. This does give you a more realistic value. For beams, you are between 25% of I gross, plug in all of this, less than or equal to half of I gross. Where a column, okay, this is actually a different section. So this gives you more accurate values. Now, is it really needed to have more accurate values? It kind of depends on what you're doing. I have a sneaky suspicion most folks just go with 70% and 35% and just run with it. But I suppose if you're doing a very important building or a very expensive building, then it might be worth the extra effort to get the more accurate values. Does that make sense to everybody? And I know Edgemon is about to ask me, do I have to use these or can I use the simpler ones? And the answer is, if I don't say anything, just go with 70% for columns, 35% for beams.
Got answer.
Right? Isn't you're about to ask that, weren't you?
I was about to ask that. Bear with me a second. That wasn't somebody else. That was one of my students. So, okay. Now, so this is a different section. This part was talking about columns are cracked, so don't use I gross, use 70% of I gross. Beams are even more cracked, so don't use I gross, use 35% of I gross when calculating the psi factor. Remember, this is all we're doing right now. We're just calculating a psi factor so that we can determine the value of K. The value of K is needed for the unbraced length in determining slenderness ratios. Okay, so where a column bears onto a concrete footing, we have a different procedure for determining psi. And I'm not sure, I don't think this part of it's in the textbook. So if it's not in the textbook, just reference my lecture notes for this part of it. But we still need a psi value for where the column meets a footing. And it's not where a concrete column meets a concrete footing cannot automatically be assumed to be fixed. It may not be fixed. It totally depends on the properties of the soil, and it depends on the size of the concrete footing. You know, you could have a really stiff column coming onto a fairly small footing, and that footing will just roll over, and it's not like it's fixed at all. Or you could have a really wet noodle of a column coming into a huge footing, and it's practically fixed, right? So you have the whole spectrum. So the way we do it is we calculate the stiffness of the column over the stiffness of the footing. And the stiffness of the footing is considered to be the moment of inertia of the footing times this Ks factor, where I sub F is the moment of inertia of the footing in inches to the fourth in plan view in the direction in question. And don't worry, I have an example for this, but this is moment of inertia in plan view, and make sure you're doing it in the direction in question, because we could be looking at this in the north-south, we could be looking at this in east-west. K sub S is a coefficient of subgrade reaction, soil stiffness, units of which are KSI per inch. This is a reference that I got. This actually came out of the PCI Design Handbook. But here's some examples of a correlation between K sub S and allowable soil bearing pressure that you can approximate with. So you can approximate K sub S from allowable soil pressure given a typical soils report. For the purposes of this class, you can just assume K sub S is equal to, that's actually 120 PSI per inch or 0.12 KSI per inch. Okay, and the alignment chart itself is figure reference 6.2.5 on page 65 of ACI 318, as well as figure 11.3 on page 317 of the textbook. And it looks like this. We have one for braced frames, and we have another for unbraced frames. And we have a psi A and a psi B. Okay, so if we have this situation, here's my frame, this is my column in question.
It is braced against side sway, as is labeled here. We don't really need to know what the rest of the structure looks like. It suffices to say that it's braced. The beam section is here. It's a 20-inch wide by 36-inch deep beam. And the column section is here. It's a 20 by 20 column. The footing is a 24-inch deep, 6 foot by 8 foot footing, and the 8 foot is in the direction of loading. Center to center is 24 feet and 27 feet for the beam. What I want to know is, what is my K factor? Use the alignment charts to find your K factor. Use table 66311A for effective moments of inertia. Solution. So we're going to find psi A at the top of the column. This is the sum of all the columns coming into the top joint over the sum of all the beams coming into the top joint. My modulus elasticity is 57,000 times the square root of F prime C, which is 4,031 KSI. I, for the column, is 70% of the moment of inertia of the column, IG, which is 70% of 20 times 20 to the third over 12, 9,333. See, so this is the simpler way to do it. Just use 70% of I gross. And L sub C for the column is 24, center to the bottom of the column, which is 288 inches. Okay, now for the beam, we're going to use 35% of I gross, or 35% of 20 times 36 to the third over 12, 27,216. So the center to center spacing is 27 feet, or 324 inches. Assume columns and beams are all poured with the same concrete, so E is the same for both columns and beams, so it drops out of this equation. And therefore, psi A is equal to 4,031 times the 9333 over the length of 288 over 4,031 times 27,216 over 324 is the length, and I get 0.386. That's psi A. Find psi B at the bottom of the column at the footing. So the equation is the sum of the stiffness of the columns over the stiffness of the footing. Again, E is 4,031. I is 9333, as we just found. The length of the column is 288. For the footing moment of inertia, H is the planned dimension in the direction of the frame, which was the 8 feet. So I have 6 feet is the width, 8 feet is the height over 12. I have 5,308,400 inches to the fourth. K sub S is 0.120 KSI per inch. And again, remember guys, when you're doing these equations, make sure that you have all your units consistent. This is a classic place where this could really get messed up. I have converted everything to either KSI or inches. Okay. And so psi B is equal to the sum of the stiffness of the column or the stiffness of the beam, of the footing. And I plug in all my numbers. And again, everything is KSI or inches. That's why I have this very large number, because it's all inches to the fourth. And I get 0.820. Okay, so now as I defined my problem, the problem is an unbraced column. So I use this half for braced frames. I'm sorry, did I just say unbraced? It's a braced frame. So I use this half of the chart for my braced frames. And I plot the 3.38 that I got here, and I plot the 0.8 that I got here. Where it hits this vertical axis, that is my K value. And in this case, my K value is about 0.70. The column from practical purposes is considered to be fixed with K equal to 0.70. Okay, so that's example number 1. Now I had a question, I'm not quite sure how to answer it. The trident equations are size. So you might have missed some of what I said. I can only repeat it very quickly. What we are trying to do is we're designing slender columns. For slender columns, we haven't got there yet, but you're gonna have to know what the effective length of the column is. The effective length is K times the real length. K is defined by the degree of fixed or pinned of the column. We can approximate K from whichever one of the charts that I went through in these notes that is closest to that, or we use the, I just totally blanked out on the charts, alignment charts, or we can use alignment charts. Alignment charts require the use of psi A and psi B. Psi is defined as the stiffness of the columns divided by the stiffness of the beams. The stiffness of the columns is E times I over L, the length. The stiffness of the beams is E times I over L, the length of the beams. And then you divide one by the other, and you get a psi value at one end, a psi value at the other end, draw the line between them, and where it intersects the vertical axis, that is your K value. And that's as far as we've gotten so far. Okay, time for a break, everybody?
Yes, please.
All righty, let us reconvene then. Let's meet back here at 6:15. And we'll go from 6:15 till the end at 7:05. All right, we are back from break. And so we can start with example number 2. Okay, so now we're going to look at what happens when a frame is not braced. F prime C is 5,000 psi, Fy is 60 ksi, and here we have basically the same frame, but without it being braced. So got the same center to center spacing of the beam, same center to center of the column, same footing, same cross-sectional dimensions. What is required? Let's use the alignment charts to find the K factor. Use table 66311A for effective moments of inertia. Solution. So again, we need to find psi A at the top of the column. Psi A is the sum of the stiffness of columns over the sum of the stiffness of the beams. And so I plug in the same numbers I had from example number 1. This is 70% of the gross moment of inertia of the column. This is 35% of the gross moment of inertia of the beams. And we get 0.386. Find psi B at the bottom of the column at the footing. And we're kind of repeating the same numbers, 0.82. So 0.386 and 0.82 are the same values for psi as we had for the braced frame. But now we're going to the unbraced frame side and plotting. So here we are, our 0.382 and 0.8, and see how it crosses now at just a bit under 1.2. So from the alignment chart, K is equal to 1.18. For a fixed side sway condition, K is theoretically 1.0. K suggested is 1.2. So we're right there in the ballpark. Oh, I kind of,
Professor?
yeah.
Does this work for 2 and 3 story frames too, or is just for 1 story, this chart?
No, this chart is for any number of stories. And I'm glad you asked that question. When we design columns, let me draw a little sketch here. Okay, so this is a 3-story column, right? But when we design columns, we don't look at it like a 3-story column, really. And I'm drawing into beams here. Okay, now let me use my little lighting tool here. Technically speaking, when I design this column, I am actually designing 3 columns. This column is a different design than this column, a different design than this column. Even though this is all one continuous piece of concrete, or even if it's precast, it literally is one piece of concrete, but design-wise, it's 3 independent columns. And if this is braced or unbraced, either way, you're going to get a different effective length here than you have here because this is a different support condition than this is. So when designing the bottom column, let's use this. I think it goes like that. Okay, so when designing this column, this is psi A and this is psi B. This is psi A and this is psi B for this stick of column. But when I go to design this column, this is psi A, this is psi B. When I design this column, this becomes psi A, this becomes psi B. Each column is designed story to story. Does that make sense?
Yes, it makes sense now. Thank you.
Okay, good. Okay, so now let's talk about slenderness ratio. This is actually, we're moving on to the next topic. So we've calculated how to come up with K, but that's still not the whole story. We need a slenderness ratio. So to get that, we're going to use R. R is the radius of gyration. ACI A318 section 6251 allows R to be taken as the square root of the gross moment of inertia over the gross area, or you can take it as just 0.3 times h, where h is the dimension of a rectangular column in the direction of loading. This comes out to be very close to 0.3. You can use 0.25 d if d is the diameter of a circular column. The slenderness ratio is defined as KL over R. So you could have a really long column, but if it's a really stout and stiff column, then it actually might be less slender than a fairly short column that is really, really like a wet noodle. So a perfect example, you could have a 12-inch by 12-inch column that is going from the ground floor up to a balcony. So maybe it's 15 feet long, but it's only a 12-inch by 12-inch column. That 15-foot long column very well be more slender than the column supporting the 71 freeway going over the 10 freeway that's like 120 feet up in the air, because that column is 8 feet in diameter. So does that make sense? How slender a column is in proportion to its effective length over this radius of gyration. So slenderness effects may be ignored if your calculated KL over R ratio is less than or equal to 34 plus 12 times M1 over M2. Remember, M1 is always the lesser moment, M2 is the greater moment for braced or non-sway columns. Also, you might want to make a note, M1 and M2 are the factored moments. We're back to factored moment design. So M1 is factored, M2 is factored. And so if it's less than this number and it's less than 40, then you can ignore slenderness if it meets both of these criteria. Or if KL over R is less than 22 for an unbraced or sway column. So the restriction on when you can ignore slenderness is much, much tighter for unbraced columns, where M1 is the smaller end moment, M2 is the larger end moment. And so here's what we're talking about. M1 is the smaller moment, M2 is the larger moment. The ratio M1 to M2 is positive for a single curvature. And the ratio of M1 over M2 is negative for double curvature. And this is actually much more common in the real world. I've come across this fairly rarely. This is almost every day. Actually, let me back up a little bit. Okay, so see how I'm saying M1 over M2 is positive for single curvature, M1 over M2 is negative for double curvature. That applies in this equation right here. So this is 34 plus 12, and if M1 over M2 is single curvature, then this is positive. So KL over R has to be less than basically 46 or 40. But if M1 over M2 is negative, that's double curvature. And that means that this is a lower value, because this would be 34 minus some value here, that it has to be less than. Okay, so in this equation here, be mindful that M1 over M2, that overall effect could be positive or negative, depending on if you have this or if you have this. Any questions about that?
Is that because the beam, not the beam, sorry, the column is going to buckle in two different directions? That's why it needs to be more slender. That's why we're going to get less value.
It actually has to do with the shape. Remember the very first slide I did. If I take a column and I bend it and I bend it, then this column is going to bend into this shape. And the maximum deflection of that shape is right there. And so the P delta effect is pretty dramatic right there. But this column doesn't bend into this shape. This column bends into this shape, like this. And because this is bending it that way, and this one is bending it the opposite way, the maximum deflection is it's probably down here where M2 is bigger, but the maximum deflection is much smaller than the maximum deflection from single curvature, because these two add to each other like a double whammy. These two take away from each other, so the actual maximum deflection at the midspan is quite minimal. So this is much better of a situation for P delta than this situation. So in this case, so in this case, M1 over M2 positive hurts you, M1 over M2 negative helps you.
Makes sense. Thank you.
Okay. Perfect. Okay. Okay. Now we have this thing called a moment gradient effect. Per ACI 318-66453 defines C sub m as per A or B. And by the way, this is the same C sub m that you would find in steel design. Steel design has a moment gradient effect as well. For columns without transverse loads applied between supports, Cm is equal to 0.6 minus 0.4 times m1 over m2. And again, the ratio m1 over m2 is positive for single curvature, negative for double curvature. For columns with transverse loads, Cm is equal to 1. And let me, just in case it's not clear, this is my design column, and if all I have are end moments like this, then this is columns without transverse loads applied between supports. But if I had a column where for whatever reason, I had some loading like this, see, now this would be loading between supports. So my column with transverse loads, Cm would be equal to 1 in this case. Does that make sense to everybody? Okay.
Yeah, it kind of does.
Okay. So what is this Cm factor? Why is it there? And, oh, if there are no end moments, then Cm is also equal to 1. Cm equal to 1 is conservative and can be used if in doubt. Okay, so what is that moment magnifier doing? It kind of goes back to this idea. If this is my column, then if the deflected shape looks like this, then that is the worst possible condition, because then my delta here is very large, and the P delta effect causes moments that cause more deflection, which causes more slenderness effects. But if I had a moment diagram that looked maybe something like this, see, now the deflection at midspan is less than the maximum deflection over here. So when the column starts to buckle, it's going to take a shape that looks like this. And so the maximum buckled deflection is not coinciding with the maximum moment from the loading. So they don't add directly to each other. So you get a break, you get a fraction that's less than 1. If you had a moment diagram that causes a moment like this, and then you had a P delta, which causes a deflection like this, the worst of both occur in the same place. And so Cm then is equal to 1. They directly add to each other. That's the idea of this moment gradient. Okay, so all of this leads up to our moment magnifier delta. Moment delta, or I'm sorry, magnifier delta is based on Euler's equation for the buckling load. ACI 318 section 66442 defines the critical buckling load as P sub C, that is my critical buckling load, that's axial load in kips, is equal to pi squared EI effective over KLU squared, where K is defined previously. For non-sway, K can be conservatively taken as 1, but sway columns must be at least 1, usually more. EI effective is defined by ACI 318 66444 as one of A, B, or C. A, EI effective is 0.4 ECIG over 1 plus beta DNS, or 0.2 ECIG plus ESISE over 1 plus beta DNS, or it is the EI over 1 plus beta DNS. This is kind of strange, isn't it? Why are we redefining EI effective? And what is this all about? Well, we just previously said that I could take I to be 70% of I gross, but that's only for the determination of the psi values. Now, the stiffness of the column is really, really important as to how much load it can take before it buckles. So they want us to do a little bit more work here and try to get a better approximation of what the actual stiffness is. So in these three equations, and it doesn't say that it's the least or the greatest, it just says use one of these three. Whichever one of these three you choose to use one of these three. So in all three of them, we have this beta DNS value. What is this? This is the ratio of the sustained factored load over the total factored load. So this is axial load. And it kind of gives you an idea how much of the load is there all the time over the total design load. ISE is the moment of inertia about the centroidal axis of the member for the steel. And I is this, going back to this equation here, where you have to calculate all this stuff somewhere between 35 and 8.875 I gross. So at first you're looking at this going, oh yeah, well this is the easiest one, right? I'll just do this one. And not so fast, because this one, this I is this equation down here. So really of these three, this guy here is probably the easiest one to apply. Any questions about that?
Do they all give you the same value?
No,
Oh,
no. Nobody said they're equivalent.
I'm very confused now.
Okay. Remember what I said, like in the first time we met. Everything we do in concrete, we are creating models that tries to predict what concrete wants to do. And some models are better, some models are not so good. But everything we do is just an approximation. It's a model trying to predict something that is massively complex. And this is no exception. So what the code is saying is use model A or model B or model C. It's up to you. Which one do you want to use? They will all give you different values, not vastly different values, but they will be different values. And the code says any one of the three is accurate enough, you can choose which one you want to use. But as a designer, if you do this for a living, you can program this stuff into spreadsheets and Excel and whatever. So you don't need to be daunted by the complicatedness of this. You can program this stuff in and let the computer do it for you, as long as you know you're doing it right. And so as a designer, sometimes I might take the most complicated approach because I have resources to plug it in, and I'm not trying to do it by hand every time. And it might be to my advantage to use the most accurate version that I have available. Or you may be doing it by hand, or you may just be doing a rough design that you're going to fine tune later, and you don't want this degree of accuracy. Maybe then you just want the quickest and easiest one. So the code gives several options at different times, and just understand that none of these are the exact answer. None of them are. In fact, there is no exact answer because concrete is what it is. It just defies exactness, but these will get you close. So did I help with the confusion? I know this can be very confusing, but they're just different approaches that the code said, if you want more accuracy, use this one. If you want quick and dirty, use this one. If you want something in between, okay, use the middle one. Does that make sense?
Got it. No, thank you.
Okay, great. Okay, so for non-sway columns, ACI 318 66451, the factored design moment, MC, is equal to delta times M2. Concrete, yeah. So, and I'm using the nomenclature directly out of the code. So it lists this as MC is equal to delta M2, where M2 is equal to the larger of each end moment. And so basically, what are we doing here? We're coming up with a design load that we designed to, that is an amplified version of the original load to account for the slenderness. So my design load becomes my load that I had applied times this delta that we are going to evaluate, where M2 is equal to the larger of each end moment. But one more complication, ACI 66454 prescribes that we have a minimum moment equal to the axial load times 0.6 plus 0.03 times h, where h is the width of the column. So if you can imagine if you have a column and by design, you could have 200, 300 kips of axial load on it, and you think you have no moments on it. If you had exactly 0 moments, then it's not going to ever buckle, because buckling is the amplification of the applied moment. So 1,000,000 times 0 is still a 0. But you never actually ever have a column that has exactly 0 moment on it. There's always some accidental built-in eccentricity. So the code addresses that and prescribes this minimum moment if the actual applied moments are too small. So please keep that in mind, that when evaluating this, if this moment is small, it may be that you have to plug in this as a minimum. Okay, and now to the equation. 66452 gives the moment magnification factor as delta is equal to Cm over 1 minus your applied load Pu over 0.75 PC, which is the Euler buckling, critical buckling load, which has to be greater than or equal to 1, okay? So you will never have a moment magnification factor that actually is less than 1, and that would actually make the load, the moment, smaller than what you have. That can't happen. So delta is either equal to 1 or more. Okay, so example. Here we have our frame again. Only this time I've given you a pin support at the bottom. It is fixed at the top by this beam, and I have an axial load and I have an applied moment. Concrete is 4,000 PSI. The steel yield is 60 KSI. And my axial load is 800 kips. 550 of that is sustained. And my applied moment here at the top is 80 kip feet. What is required? Determine if the given column is adequate with the given loading. Solution. Firstly, we have to create a column interaction diagram by calculating and plotting our 5 points. Pure compression, 0 tension at the tensile steel, our balance condition, fully yielded, epsilon sub t equal to 0.005, and with 0 axial load or pure moment. Okay, so we're going to do this. We're going to go through our 5 points. Before I do that, let's go back. Now, remember, here's our column here. It's a 20 by 20 with, that's really, really small, but I think I got 8 number 7s. So 4 number 7s on each side, 20 by 20 column. Point 1, pure compression. So this is kind of a review of what we did for short columns. P naught is 0.85 F prime C AG minus AST plus FY AST. AG is 20 by 20, 400 inches squared. AST is 8 times, number 7 bars, is 4.8 inches squared. P naught, I plug in my values, and I get 1,632 kips. I was going to briefly mention, we've already done point A through D on a previous lecture. So I'm going to try to not read off every number in here for time's sake, as we only have about 20 minutes left. But these are the same equations that we used before. Is everybody okay with that? Is anybody not okay with that? All right, so from committee work that I do, if I have no nays, it passes unless I don't have a quorum, which means that nobody's listening.
Professor, we're fine with that. I mean, I'm fine with that.
Listening.
It's good.
We're good.
We have a quorum. Awesome. All right, we're going to go through this. Pn is 0.8 P naught because this is a tied column. This is not a spiral column, so that's 0.8. So I have 0.8 times 1632, 1305 kips. My phi Pn is 0.65 times Pn. Again, this is tied, so this is 0.65, not 0.7. 0.65, 1305. I have a capacity of 848 kips. And remember, for the purposes of drawing the diagram, it's also useful to know where phi P naught is, and that's 1,061 kips. Mn by definition for pure compression is 0. Point 2, zero tension. C is equal to D. You remember from the last lecture, we had those diagrams showing the strain and the stress and all that. So kind of going through this a little quicker. C for zero tension is equal to D. 20 minus 2.5 is 17.5. Oh, I did draw the diagram. Beta 1 is 0.85 from our table for 4,000 PSI concrete. A is beta 1C, which is 14.88 inches. C for compression, C sub C is 0.85 F prime C, gross area minus the area of steel. So I plug in my 4,000, my 1488, 20 wide. Half of my steel is in the compression zone, and I have 1,003.7 kips. So C sub S is F prime S times AST, but has compression steel yielded? From similar triangles, epsilon C over C is epsilon prime S over C minus 2.5. I plug in my numbers. I get 0.00257 greater than the yield. Yield is 0.00207. Therefore, compression steel has yielded. And so I can just plug in 60 times the area of steel, 144 kips. Sum the forces in the vertical direction to solve for Pn. Here's my force diagram. And my Pn is equal to 1,147.7 kips. Define Mn, I sum the moments about the right-hand side of that diagram. I have Pn times h over 2 plus C sub C, A over 2 minus C sub That's supposed to be C sub S again. I can't believe it came over from the other lecture. Anyway, tension, or I'm sorry, axial load times half of the column plus the compression in the concrete times A over 2 plus the compression in the steel times D prime is 3,649 kip inch, 304.1 kip feet. Since epsilon t is less than epsilon y, it's actually equal to 0. Then phi is 0.65. Vpn is 0.65 pn, which is 746 kips. Vmn is 0.65 mn, which is 198 kip feet. So that's point B. Do I have any questions so far? Okay.
Professor, you didn't show
Yeah.
the calculations for the epsilon t, right?
That's right.
Okay. Okay.
I did not show the calculations because, oh my gosh. Sorry about that. I did not show the calculations for epsilon t because point B is defined as zero tension at the tension steel. So by definition, epsilon sub t is equal to 0 for point B.
Makes sense. Thank you.
Okay, and I was right here. Okay. Guys, bear with me just a second. I have to give my cell phone to my wife. I'll be right back. Okay. Sorry about that. Normally, I would not let a cell phone call interrupt my class, but my father is ill, and we have to go up to take care of him tomorrow. So it's kind of important that my wife takes that call. So sorry about that. And we are running short on time. Let's see how far we can get. Point C is the balance condition. Everybody remember the definition of the balance condition? Okay, the balance condition is a loading that creates a strain condition where the concrete reaches 003, the crushing strain, just as the steel reaches yield, which is 00207. So the steel yields at precisely the same time as the concrete reaches crushing strain 003. So that's the definition of the balance condition. Okay, so we can use similar triangles, and epsilon sub c over c is equal to epsilon sub s plus epsilon c over d. And here's our diagram. So epsilon sub s or epsilon sub t we know is 00207. Concrete we know is 003. What we don't know is what c is. So we use this to solve for c. C is equal then, and I plug in all my values, 10.36 inches. A is beta 1 times C. 0.85 times 10.36 is 8.80 inches. So C sub C, the compression in the concrete. And again, I plug in the same values, but A is 8.8, the width is 20, the steel on one side is 2.4. I get 590.2 kips for compression in the concrete. Epsilon prime S is by similar triangles now. 10.36 minus 2.5 times 003 over 10.36 is 00228. So the compression steel has yielded. So F prime S is 60 KSI. So the force in the compression steel is 60 KSI times the area, 2.4, is 144.0 kips. T is the Fy AST. Now again, our definition is that the steel has just yielded. So that means that the tension steel is also 60 KSI times 2.4. It's also 144.0 kips. So now I have all the pieces. I have my tension. Actually, I don't have PN, but I have my tension, my compression in the concrete, my compression in the steel, and the only thing I need to solve for is PN. So PN is equal to 590.2 plus 144 minus 144 is 590.2. To find M sub n, sum your moments about the right side edge here, and we get Mn is 5. So again, tension times H over 2, compression in the concrete times A over 2, minus the tension in the steel, no, I'm sorry, minus the compression in the steel times D prime, plus the tension in the steel times D. Now, you may be tempted to say that the axial load 590 is the same as the compression in the concrete, so they cancel each other. And the load in the tension steel is the same as the load in the compression steel, so they cancel each other. But they do not cancel each other because their effective moment arms are very, very different. So we get 5465 kip inches or 455.4 kip feet. Since epsilon t is equal to epsilon y, then phi is still 0.65. Remember, epsilon t has to be greater than 0.004 before phi even starts coming up at all. So phi PN is 0.65 PN, 0.65 590 is 384. Phi MN is 0.65 MN, 296. Okay, so that was point C. Any questions on point C? Okay. Point D is where epsilon t is equal to 0.005. That's we define that point by this benchmark. So by definition, the tensile steel has yielded. From similar triangles, epsilon c over c is equal to epsilon s plus epsilon c over d. We know everything else, so we solve for c. C is 6.56 inches. Here's my strain diagram again. Very similar before, but now this is 0.005, so C is getting smaller. A is beta 1 times C, 5.58 inches. C sub C, and we have the same 0.85, 4,000, but A is 5.58 minus area steel, 371.3 kips. Epsilon prime S, we plug in C into here and here, and we get 0.00186. The compression steel has not yielded. So I can solve for it by the strain times 29,000 KSI, basically Hooke's law. Stress is equal to strain times modulus, 53.84 KSI. So the compression in the compression steel is 5384 times 2.4 inches, 129.2 kips. T, now Fy has clearly yielded because it's at 0.005. So we have 60 times 2.4 is 144 kips. Sum the forces in the vertical direction to find P sub n. And we have P sub n is 356.5 kips. To find M, sum the moments about the right-hand edge. You can see we're kind of developing a procedure here. We keep repeating the same procedure. And this is Pn times H over 2 minus T times minus the compression in the concrete times A over 2 minus compression in the steel times D prime minus the tension in the steel times D is 4726 or 393.8 kip feet. Since epsilon t is greater than 0.005, phi is now equal to 0.9. So phi pn is 0.9 times pn, 321 kips. Phi mn is 0.9 times mn, 354 kip feet. Any questions on point D? Okay, so point E is 0 axial load. Problem becomes a compression steel beam problem. Rho is 2.4 over width times D, 0.00686. Rho prime, same thing, 0.00686. So if rho minus rho prime was greater than this number, then the compression steel would yield. Clearly it is not because they're equal to each other, so the steel will not yield. So we have to write our force equations in terms of little c. So the compression in the steel, F sub s, can be written as the area of steel times 87 KSI C minus D prime over C. And this simplifies to about there. It's about as simple as you get. Tension is area of steel times Fy. So that's 144 kips. Compression 0.85 F prime C B A is equal to 0.85 F prime C B beta 1 C. Plug in all the numbers we know. That's 57.8 kip per inch times C. Summate them to equal to 0. Solve your quadratic. C is equal to 2.50 inches. A then is equal to beta 1 times C. 0.85 times 2.5 is 2.12 inches. Therefore, F sub S is C minus D prime over C is equal to 0 KSI. It actually, if you look at this, C is at 2.5, your steel is at 2.5. So the neutral axis is actually crossing right where the compression steel is. So you have 0 KSI in your compression steel. Your compression steel then is equal to 0. Tension steel is 144. Compression in the concrete, 0.85 F prime C BA is 144.3 kips. And then we sum our moments and we get 197.3 kip feet. Phi-mn is 0.9, so I get 178 kip feet is my Phi-mn. Pn, by definition, we said no axial load, so Pn is equal to 0. And all of that was to create this diagram. So here's all those points we just did. This was point A. This was also point A. We needed this point to find where these two intersect at this point here. This was point B, C, D, and E. So we have this whole diagram now. The slenderness, this is the way ACI makes this work. The slenderness is not going to change this diagram. What the slenderness is going to do is take your applied load and amplify it. And it may amplify your applied moments right outside of that curve, in which case the column doesn't work. Or it may amplify your moments inside of the curve, but it still works. Okay? So we don't know that yet. But the whole slenderness deal does not change your interaction equation. It changes your applied loading. Okay? And you're just going to have to wait till Thursday to see if it works or not. So do we have any parting questions for me before we close it up for this evening? You know what? I just realized something, guys. That's my last slide. We finished. I forgot I broke this lecture up into 2 lectures. So this is it. We made it with 3 minutes to spare. That's fantastic. Okay, so next time we're going to start with lecture 13, and we're going to carry on the same example, but we're going to find our magnified moments due to slenderness. Okay, so as I said, do we have any questions for this evening?
For me, not yet.
Okay. All right. So we will continue next time. My next lecture will pick up where this one left off, and we will work through the moment magnifying and see if those lows actually work or do not work with this applied column. So with that, I'm going to close this session, and I will put the recording on YouTube as soon as I get that opportunity. Thank you, everybody, and we'll talk to you on Thursday.
Thank you, Professor.
Thank you.